Okay, guys, we're going to get started on our fifth presentation. Sorry to say I'm back up here again. So last time I was up here, we were talking about the different cloud structures that Expedient has, being private, public, and hybrid. The latest announcement we have is that in the last year, in 2016, we put together an on-premise cloud where we're actually bringing the cloud infrastructure to the customer's data center. Not everybody has the ability or the desire to leave their data centers. Sometimes it's compliance issues. Sometimes it's just nervousness over where they have their product. Sometimes it's latency issues based upon what the application is. So what we have done is the infrastructure that we build, we have the ability now to put it on customer premise and manage it just as an extension of our existing network of data centers. So exciting stuff. We fully expect that to be a really good product for us moving forward. So our fifth topic, big data. If you're not collecting it, you're not benefiting from it. So let's bring up to the stage. We have Richard Brueggman, CEO of Data Science Automation, and Jeff Christensen, who is VP of Products from Seegrid.
Thanks, Dave.
Thank you, thank you. There you go. See?
Just going for the, let's make sure this works. All right. So, yeah, thanks for joining us this afternoon. I think people in the data science realm might think that everybody coming up through the ranks now that might be following in our footsteps, so to speak, they're chasing robotics and, driverless vehicles and things of that sort. But my daughter alerted me this morning that her high school has a big data club. So it's already getting that far down into the younger kids. So anyway, we're going to talk about big data and not from the traditional sense that you've heard it presented in earlier today in all these other sessions where they're maybe talking about how to manage the data. But we're talking more about how to actually get the data and then how we might apply it in a couple real-world examples, more on the manufacturing, R&D sides of things rather than in retail or those types of applications that have been discussed earlier today. So this is, you're supposed to start with a joke, right? But this isn't all that funny. We're talking about best practices. That's what our presentation is going to be geared to. And really, we've been doing 25 years of implementing best practices along the lines of automated data collection with the likes of Seegrid and other leading manufacturers, both in this region and domestically, internationally too. So anyway, you start with Peter Drucker. You got to start with a quote, like the other guy was saying. And one of the management gurus, he had a saying that if you can't measure it, you can't improve it, you can't manage it, et cetera. And I'd maybe alter that a little bit and say, if you don't measure it, you won't be able to improve it. And so part of our presentation today is going to be talking a little bit about that missing data that you're probably not getting that you might want to start thinking about. And we go a step further too. It's not just about measuring the data, but we want to try to get you to start thinking in terms of getting those measurements in more of an automated way so that it's not so labor intensive. Get rid of clipboards. I mean, you think in this day and age people wouldn't have clipboards, but you already heard several presentations today where they do have clipboards in a lot of places, and it's just kind of silly. So we want to get to a point where we're automating the measurements so that you can get more reliable, consistent data that results in those big data repositories. So kind of the objectives, might think for yourself about, what are your biggest big data challenges? We can talk about the missing data that might be meaningful, how to automatically collect that data, and how to benefit from the data once you have it. Okay. So I want you to think a little bit about where you might be in the product development lifecycle. And as I mentioned before, we're talking more about product and process development initiatives, more so than some of the other types of presentations you've heard today. But this is conceptually the different stages that you might go through if you're trying to develop a new product or process. You're going to research. You're going to prototype, manufacture, test, and distribute. And I'm not going to read all of that, but as an example, in the research phase, we've worked with customers who want to automate drug discovery, and so rather than maybe using computational science and chemistry to determine what the right drug regimen should be, they want to just try every option. Right, just literally try it. And so we get into systems where we're doing high throughput screening of drug recipes, formulations, and you can test a lot more. You can cover a lot more ground than you might be able to cover just mathematically. Another example, if you're going into prototyping, I'm going to talk a little bit more about this later, in the Tomahawk missiles that the military uses. A lot of work goes into doing hardware-in-the-loop simulation of those products, because you can't just say, oh, well, we have a missile here, let's press the go button and see if it hits its target. Like, you can't really just try that, right? You want to, not internationally, you might be able to try it domestically, but so you got to do a lot of simulation work, and high amounts of data might be involved. On the manufacturing side, there's examples of that too, but you're essentially trying to do condition monitoring, do predictive maintenance so that you can limit downtimes, maybe more on a scheduled basis. Automated testing type applications and distribution of products. I give you another example. We work with a lot of the respirator manufacturers. Ever since 9/11 hit, everybody, all first responders had to be outfitted with CBNR, chemical, biological, nuclear, radioactive threat respirators. And all the world's leading manufacturers have to, there's a lot of parts that go into them, and they need to test them and trace every component that goes into those respirators across a wide distribution network, and so they can manage recalls more quickly and things of that sort. So traceability becomes a really important part in the big data picture. So those are some examples across the product development life cycle. So I'll talk for a moment and get some of Jeff's input too here about what data you might be missing. As examples, what are you ignoring? Because if you're not collecting it, you're ignoring it, right? Because today, well, I'll let you go, Jeff. Sorry.
No, I think that's right. So, Rich is obviously from DSA, and I'm from Seegrid, and so Seegrid we make autonomous vehicles. Speaking of the robotics and driverless cars that are the fancy stuff, so some of that is happening as well. But one of the things that I look at in designing systems, whether it's software or hardware systems, is how to instrument it very early on. Right, so think about all of the different either physical actual moving parts or virtual moving parts in a software system, and what are the things that you want to instrument early, and don't edit yourself too early in the process, because you don't know what data you're going to want on the other end. So, so the ignoring data, you may be ignoring data that exists just or would have existed had you collected it, right? The data exists. It's whether or not you decided to instrument it and collect it early enough in order to be able to go back and look at something. So as you're designing a system, whether it is a software control system for a missile or for a vehicle or for just a software-only system or things like that, think about the important points of interaction and inflection points within that system, and consider instrumentation early. So by instrumentation, I mean, all right, I'm going to log that, I'm going to log that, I'm going to log that, and I'm going to collect more data than I think that I will actually need, because it will surprise you later on what kind of insights you can get from the data that you sort of accidentally collected. So some of that data that may be ignored, it was there all along. It's just a question of, did you think to collect it beforehand, before you knew you needed it?
And nowadays, it's not all that expensive to be recording it, collecting the data. I mean, sensors aren't very expensive. If you're buying the instrumentation to acquire all that data from a handful of sensors, it doesn't cost much more to now instrument it for, you know, dozens of additional sensors. So like Jeff's saying, let's collect everything you can, and you can worry about what isn't necessary later, right? What doesn't correlate. So keep going. So when we talk about collecting big data, this is kind of the science, or the more traditional science, that comes before the data science, okay? So you have to acquire the data somehow, and so what data are we even talking about? Let's go back to the very beginning, and it's some type of physical phenomenon, usually. In my world, as we're talking about product and process process systems, we're talking about acquiring things like temperature or measuring heat, right? And you're trying to measure absence or presence. Is something near or far? Is it even there? You know, live video feeds to tell you what's going on in the process. Measuring dimensional data around a part that might be coming down a production line. Doing biometrics. Now, there's a lot of that kind of stuff. These are all sources of data, physical phenomena that exist out there, that there are sensors and technologies that will allow you to acquire that data. And so, but that's only a piece of it. Acquiring it requires then, you know, some form of sensor to convert that physical phenomenon into an electrical signal that the computer can then recognize. It's not typically that simple, though, right? We end up having to get involved in some type of signal conditioning. Signal conditionings can be things like amplifying the signal. For a low-level signal, you want to amplify it a lot so it's above the signal-to-noise ratio before you digitize it and get it into some meaningful data that the computer can utilize. You may have to attenuate it, isolate, filter, do some type of signal processing on the data prior to getting it into the computer. Now, to get it there, you need typically some type of A to D, that stands for analog to digital converter. So electronics, a board of some sort that does that conversion. You can plug it into your computer, it can sit remotely. But you've got these sensors through the signal conditioning wired up to some type of digitizer, which then takes what we would call an analog signal, continuously varying signal, like temperature, and convert it into a digitized signal that's now discrete, right? It's got thresholds that it goes through, and the higher resolution digitization that you can do, the more accurately you can represent that continuously varying signal. So that's some of the engineering and science that has to occur to sample all of those different, and this is by no means an exhaustive list, to sample all of these different phenomena, okay? So once you have the signal digitized, it's in the computer, you can then route that data to various different sources, repositories, or whatever. And I'll get to another slide that'll continue this in a moment. But you have to go through all of that to collect the data before you can then start to benefit from it. Okay, at least the type of data we're talking about here, more sensor-based. Earlier sessions have talked more about crowd-based data, you know, where you're collecting a lot of data through the internet or through maybe electronic data interchange, the EDI transactions. This might refer to, even in the supply chain management realm, if I look at the last bullet there as an example, one of our customers wants to monitor silo levels for large manufacturing facilities, silos of plastics or powders or pellets or sand and things like that. And so you need level sensors, things to measure level. You want to transmit that data back to a central repository to do all kinds of mathematical analyses on it to determine when will that silo deplete so that I can schedule a rail car to arrive just in time, right? So that's an example of more of an elaborate EDI scheme where there's actual worldwide sensor networks designed to provide the data back to a central dispatch for those rail cars and things of that sort. So as examples. So going a step further then, benefiting, what do you really have to do? Well, you're going to analyze the data. And I've given you a few examples of that already, but it could be something as simple as averaging or trying to calculate the mean time between failures for products or filtering the data, doing regression analysis, curve fitting, et cetera. So there's a lot of different types of analytical techniques that you can do in software. Then you're going to archive data. Now, we've talked a lot about data repositories in this conference, but there hasn't been much talk about the raw data itself. So for us, we're acquiring sometimes tens of thousands of channels worth of data, watching waveforms for a long periods of time. So you get a lot of raw data, but you don't want to put all that in a database. You know, you'd be storing the raw data instead in binary files, historians, things of that sort. And then you use the metadata, the results of any analyses that may have occurred, and put that into databases for searching and metrics, traceability purposes, et cetera. Once you've got all the data stored, and I'm not going to go into mining it so much because you've heard plenty of that, and even on the visualization side, but you can get into dashboards and HMIs, human-machine interface, graphs, all of that. A lot of stuff is now mobile, so you can pull up on your iPad what the manufacturing process looks like today. You know, is my operation running at the right pace, or should I go in over the weekend and try to kick somebody's butt? So then you get into mastering, and that gets into a lot more learning and intelligence and the types of things that maybe Jeff will talk a little bit more about too as it relates to his applications. So I'll give you, see on time real quick, a couple minutes left. So here's an example, this is an example where we've built a munitions test system for the Navy. And among other things, it'll test Tomahawks. And what we do is we simulate a GPS satellite constellation so that the missile doesn't actually have to travel, across international borders and in hostile airspaces and things like that. But you have to simulate that it's going to actually hit its target, that it's going to, at any individual waypoint, it reads the GPS signals and decides, okay, now I need to reroute around the Strait of Gibraltar or whatever it is that we're trying to avoid, and then hit its mark. And so, as an example, a couple months ago, I guess it was late summer last year, the military used the Tomahawks to take out Yemen radar installations. And so you guys can think anytime you hear the Tomahawk hitting something that a Pittsburgh company actually had an impact on acquiring 20,000, in this case, 20,000 channels of data at 1,000 samples per second, roughly half a terabyte or so of data per test, to learn a lot about how those missiles operate so that they'll hit their mark when given the opportunity. Give you other examples on traceability on medical devices. This is an apheresis type machine. That's my father, actually. So I walk into the hospital, see my dad, and there he is sitting connected to a machine that's a product that we've helped test and do traceability analyses on. So it hits home when that kind of stuff happens, right? So medical devices like this spread all over the world, kind of in those local databases. We acquire every piece of data, every button click, every error code. Everything is just logged indefinitely for years, transmitted back to the mothership, so to speak, to do remote diagnostics and whatnot, and know what needs to be recalled if there's a problem. So that's another example of big data in use. And let me turn it over to Jeff again.
Yeah, and I think that I think our clock's about to run out. So these are autonomous vehicles. So we collect a lot of data there. But just to go back to that to bookend on that Drucker quote, it's one of my favorites. Is if you can't manage it if you don't measure it, or if you don't measure it, you can't manage it, whichever the order was. But what that means is that goes for anything that you're doing. It's not just a technology system. That could be a business process. That can be a marketing campaign. Any of those things. Think about how you want to measure it before or as you are designing it. So that will then put you in the mindset of instrumenting those things. So these autonomous vehicles, they log gigabytes of data. It takes images, it has 10 cameras, it's doing all of this stuff to know where it is in its environment. That's how it navigates. But it has millimeter by millimeter instrumentation of everything that it did. Now, that's a lot of logging for a for diagnostics, and that's great. But from an operational perspective, if I'm running a factory and I'm building cars, and I now have a millimeter by millimeter log of every single material move that happened in my facility, that's giving me incredible operational insights that I never had before. Right? So that's something that never would have even been possible if this was being moved around manually. So thinking about instrumenting these systems as they're being designed, and then the data that gets collected in their normal course of use, again, whether that's a process or a product or a software system or any of those things, as that data is collected in its normal course of use, you get to be sometimes predictably the beneficiary of those things, and sometimes in an unpredictable fashion, you'll be the beneficiary of those things. So, so collect data early and often. You'll be glad you did. Time.
Use your next slide. You got one more.
Oh, yeah. Well, that's just showing fancy things that you can do with it. So, all right. All right. Questions, comments? I tried to hit, right? We had to. I know it's boom. Right?
Well, there's the most important slide of all. So if you need to reach us afterwards, you want to continue this discussion, please do give us a call or an email.
Dave's got a question.
Yeah, I have a question. I have a question for Richard. You had that picture there, and you were starting with the phenomena on the one side, and then you had to massage it along the way. And that looked like a lot of work. It's like 5 steps or so.
That's why we're in business, yeah.
Well, but the question really is, do you think that's going to collapse to the point where, so you know, on the right-hand end, you've got Ethernet or Wi-Fi connection to the cloud or something, and on the left-hand end, you basically have your raw sensor, right? But it seems like having all 5 steps is a pain in the butt, and it's a lot of work, and I realize it's, you know, like you said, it's why you're in business.
Yeah.
You see that kind of stuff collapsing, so you essentially have a lot of that massaging done on board, and you have you know, an Ethernet-ready sensor, or it's, you know, sitting on some kind of a wireless network it's riding on. Right?
Yeah, I think that already exists, yes. So in some cases, it can be that simple where a single purchase gets you that entire pipe, okay? But when you start talking about large scale, that becomes pretty expensive. To distribute all that capability to every sensor, there's a lot of electronics, there's a lot of smarts in that process, and so centralizing it to some extent is still a very cost-effective approach. But that does exist. You can buy a sensor with signal conditioning on it, and it just outputs the answer, so to speak. But that's a lot more expensive than buying a thermocouple, right, and sending it through a rack of instrumentation that you've got for thousands of channels. Yeah. Yeah.
This one's for Jeff. When you're dealing with the automation perspective and sending the information, I guess, not just to itself to move around, but to get back to whatever the mothership is as far as the data that you analyze further on, how do you get past the customers' need to balance one security of, like you said, 10 cameras on a particular device, and then the other one, which is having wireless communication inside of a facility that may not have the ability to project outside?
All right. Yeah, really quickly. So the first question is the security and InfoSec and things like that from the customer's IT department. Yeah, that's there's no silver bullet there. Some of them are much more closed down than others. From my perspective, if you can demonstrate the value to them of doing it, you can get an IT waiver for doing those things. If you try to be belligerent and do it with a stick, it doesn't work so well. So do it with the carrot and not the stick. In terms of Wi-Fi bandwidth and things like that, I mean, there are ways around that. You can batch things when, you know, you can compress them, batch them. You don't have to have constant connectivity. You know, our trucks aren't navigating via Wi-Fi. They're entirely autonomous, but so they can batch their own data and then, you know, push it up when they do have comms. Yeah.
Thank you.
All right.
Okay.
Thanks.
Thanks.
Thank you. Just like that.
Good job.